Hello, ladies and gentlemen. It is David. No, I'm just kidding. Well, actually, I'm not kidding. I actually am David. Okay, you know, that was just a joke to enter the discussion. So now we're going to start off with the most basic example, okay, which is the graphing the exponential equation y equals to 2 to the x power. Okay, so the first thing we need to know is that the domain of an exponential, okay, the domain of an exponential will always be um, from negative infinity to infinity. Okay, in other words, we can find the exponential of any real number, right? So that's number one. Now, it might not be clear what the range is yet, and I'm going to address that soon, okay, before we finish this. But I want to build up some knowledge ahead of time before we address that, okay? And there's going to be a couple of other properties we're going to talk about as we move forward. Now, let's look at this graph. Let's look at this. Uh, let's draw this graph together. The first and most basic technique of graphing, as you all might know, is point plotting. We're going to plot some points to find out what's happening. Okay? So that's what we're going to do here. And it's going to give us some insight. Okay? So, for example, if I take x to be, if I take some x, then my y for that x will be given by 2 raised to the x power. So in my brain, I might think, aha, I might want to take x equals 0 because I remember from my exponential rules that if x is not 0, then x raised to the 0 power is equal to 1. So in particular, if x is 0, then what will be my y in this table? My y at x equals 0 will be 2 raised to the 0 power, which according to the exponential rule, 2 is not 0, so 2 raised to the 0 will be 1. So I can put this one in right away. Aha, right? That's very interesting. So now what about, let's say x equals, what about if I have, so now I think to myself, okay, if I want to plot it near 0 because I have a very nice value, then maybe I want to put x equals 1, x equals 2, x equals negative 1, x equals negative 2. Let's see where this gets me. So let's start off with x equals 1. Okay? So if x equals 1, then the y, the associated y for that x value, will be 2 raised to the 1 power, because that's the definition of this situation. Now, what is 2 raised to 1? What is 2 raised to the 1 power? Well, we know that if x is not 0, then x to the 1 power is nothing but x. Okay? And so in this particular case, 2 to the 1 power, that's just 2. Okay? Aha! So I know that this value is 2. It's very interesting, right? What if x is equal to 2, right? I know that's the next x value in my table. By the way, let me make a quick confession here, okay? And I want you guys to keep this confession between you guys and me. But basically, I chose these numbers because I chose these numbers and I chose the base of this exponential function so that these calculations would be very nice to make a point about some trends that we're going to see later, and to show you how these things are calculated. Okay. In actual fact, if the exponential function is very complicated, we might avail ourselves of the use of a calculator. So yes, I mean, so basically, these x values were chosen to make our lives easier, number one. And number two, they were chosen because the calculations will be very straightforward. So you'll be able to do them. And so you'll be able to follow along with me, and so that you'll see that these calculations are very easy. Because right now, more than anything, I want to emphasize what the graph is going to look like, what other information we can draw from, what the graph of the exponential is going to be, and so we can gain some basic insight. Later on, we'll look at more complicated. Examples, and things might get a little hairier. They might get a little bit hairy. Okay. But we need to start with these basic examples to develop that insight, that intuition. Okay. So what if x is equal to 2, then what will my y be at x equals 2? Well, by definition, my y will equal to 2 raised to the 2 power. Now, if you remember from the exponential rules, we know that if I have x raised to the n, this is going to be x times dot 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 times x, where I'm multiplying n copies of x, right? In this case, what does that say? That means that I'm gonna my 2's, I'm gonna have 2 copies of 2, right, being multiplied. What does that mean? That just means 2 times 2, okay? But I'm not multiplying this 2 with that 2, which is a common mistake a lot of students make. What am I doing? I'm following this rule. See, the exponent is how many copies of the number you're going to multiply together, and the x is what number you're multiplying. Here the x is 2, and here the n is 2. So just by coincidence, I'm going to be multiplying 2 copies of 2 together. And of course, we know that 2 times 2 is 4, okay? So just observe that one more time. I'm going to be multiplying 2 copies of 2 together, okay? Okay. So I get 4. Now I'm going to go backwards in the table like this. What if x is equal to negative 1? Okay? Then my y is going to equal to 2, right, to the negative 1 power. This is very interesting. See, now this is getting more interesting. How do I deal with this? Well, I know from our exponential rules that x to the negative n, x raised to a negative exponent, is equal to 1 over x raised to the positive exponent, in this case, n. So I can rewrite this expression, 2 raised to the negative 1 power, as 1 raised to the 2 to the 1 power. And we recall from before that for any base x, non-zero of course, raised to the 1 power, that's just the x itself. So 2 to the 1 is just 2. So I can see, aha, that's just 1/2. Right? Because if 2 to the 1 is 2, then the bottom is just 2. So this is 1/2. And then you can see from this discussion that we've just had that if x is equal to negative 2, like this, then my y is going to equal to 2 to the negative 2, like this. Okay? And then, because of the rule we just discussed, that's the same thing as 1 over 2 to the positive 2 power. And we already know 2 squared is 2 times 2, which is 4. So this can be simplified to 1 over 4. Okay? And so here we have 1 over 4. Okay. So now I can start plotting these points, okay? To get a feel for what this is looking like. Okay? And of course, if you guys are plotting this on paper, if you use a ruler, you'll be able to get very nice points, right? So here is 1, this is 2, negative 1, negative 2, and of course 1, 2, 3, 4, etc. So let's plot together the point 2, 4. So that means I'm going to go 2 along the x and 4 along the y. So 2, 4. Oops. Then 1, 2. So I'm going to go 1 and then 2, like this. At x equals 0, the y is 1. At x equals 0, the y is 1, so right there. At x equals negative 1, so at x equals negative 1, the y value is 1/2, so it's going to be here. Right? And at x equals negative 2, it's 1/4, so it'll be like this. Okay? This is very interesting. So now, if you notice, so the graph appears to be getting bigger and bigger on the right, and it appears to be getting smaller and smaller on the left. Now we can ask a couple of questions here. If it's coming down like this, will I reach a certain point way out here in the negative values of x, where, and actually, yeah, will I get a point, will I get an x value somewhere over here in the x where the graph will cross, right? So we want to think about that a moment. Well, let's think about this a moment. We saw that when we were calculating, like let's say y equals 2 to the x at the negative 2, we saw that the way that worked out was like this. We said, okay, if x was equal to negative 2, then our y was equal to 2 to the negative 2 power, right? And we saw that because of the exponential rules we discussed, that gave us 1 over 2 to the 2 power, right? And of course we saw that 2 to the 2 power is 4, and so that gave us 1/4. But I want you to look at this right here. Look at this. Now I want you to imagine, if I take x equals negative 100, think about this in your brain. We're not actually going to calculate what this is going to be, but I want you to see what's about to happen. Well, if x is equal to negative 100, then the associated y value of this function, or of this equation in this case, would be 2 to the negative 100, because I have to plug in the x into the expression for the equation, because that'll make it true. That'll make the equation true, right? That'll force the equation to be true, in other words. So look what happens here. 2 to the negative 100, what is that? Well, because of the exponential rule we have, we know that that'll be exactly 1 over 2 to the 100th power. Look at that. I know that 2 to the 100th power is going to be 2 times 2 times 2 times 2, with 100 copies of 2 being multiplied together. Some unbelievably gigantic number, to be sure. But it's just a product, but in the abstract, it's the product of 100 positive numbers. Remember, 2 is positive. If I multiply a positive with a positive, I get a positive. And so in this case, I'm multiplying 100 positive numbers. And if you go pair by pair, as I calculate that out, I'm going to end up multiplying. Getting, so if I have a product of 2 positives, then you can see that if I multiply the first two of those, like the 2 times 2 at the beginning, then I'm going to have 4 times the remaining 99 2's in the list. Then I can multiply the 4 times 2, I'm going to get 8. I'm going to be multiplying by the remaining 97 2's in the list. And in each case, the product that I'm going to have gotten first will be positive. The product that will remain will be positive. And so I'm going to end up with a positive number. Oh my God, that was the most confusing explanation that was the most confusing explanation everywhere. So I apologize for that. But stick with me here. But I think you can get my point here. Once I put the negative exponent, it becomes 1 over 2 to the positive exponent. And so since the base b of an exponential is always positive, then I'm going to have some large number of positive numbers being multiplied, and so that cannot help but be positive, okay? And so therefore, this expression, no matter how negative this value gets, it could be negative 1,000,000, it could be negative 1,000,000,000, it could be some gigantically negative number. When I insert it into this equation, I'm going to get 2 to that negative number, which will be 1 over 2 to that number, to the positive of that, okay, in the bottom. So, and I know if I have a positive, in this case 1, divided by a positive, that'll still be positive. It will never be 0. It's positive. No positive number can never be 0, right? And moreover, it can never be negative by the same token, because a positive divided by a positive is positive. And so we know that no matter how negative we go, no matter how far to the left on the graph we go, it will never reach 0, and it will never, basically it'll never reach 0, and it'll never go underneath. So in other words, we can see that the graph gets closer and closer, in this case, to the x-axis, okay? On the other hand, if I let the x go off to positive infinity, 2 to the x becomes bigger and bigger and bigger without cessation, okay? Because you're just multiplying by 2 every time x increases by 1, right? So if I multiply, if I take 3 here, it'll be 8. If I take 4, it'll be 16, and it'll increase forever, okay? So it'll go off to infinity. So with that discussion behind us, we're now ready to say what the range is. The range is going to be from 0 to infinity for this example, okay? Why 0? Because we see that Now, by the way, remember, when I put the open parentheses, that means we're going to get close to 0 without ever touching 0. So we're not including 0 here. Okay, it's different than if I were to have put a square bracket. If this was the square root of x, then the range would have been square bracket 0 to infinity, because we could actually achieve the 0. Here, from our argument, we know that we can't achieve the 0. Because if I take x to be some negative number, x equals negative 1,000, y equals 2 to the negative 1,000 is equal to 1 divided by 2 to the 1,000 power. And we just noticed that that's a positive divided by a positive, and so it cannot be negative, and it cannot be 0. It'll be small, and it'll be increasing. It'll be, and as big as I make the, if as big negative as I make the x, it'll get closer. That expression 2 to the negative x will get, I mean, as x get larger and larger negative, the 2 to the x will become closer and closer to 0. Okay? But it'll never touch 0. And so that's why there's the range. And also another fact I want to bring up from our discussion, you can see, though in this case, the y equals x, right, is the horizontal asymptote of this function on the left. Okay? So the exponentials will usually have a horizontal asymptote. Well, they will have a horizontal asymptote. Okay? Okay. And in this case, it'll be y equals y equals 0. Because that's the bottom of our range. And we can see that it's increasing. And it's decreasing toward that 0. And so the y equals 0 is the horizontal asymptote. And then, let me see here. And so before we end this, I want to make a couple of very key important points. Number one, this exponential 2 to the x power for any input, for any real number x, is strictly positive. It's strictly positive. It is never 0. Okay? It might get close to 0, but it's never 0. And it's strictly positive. Okay? That's an important fact that we're going to look at later, or that we might need later. Okay? And the second thing is that this is increasing. Okay? Now, what do I mean by it's increasing? Let me be precise. So what I want you to observe before we give the precise definition is that if I walk to the right hand like this, what is happening to the function? The function appears to be going up. And so that's what I mean by increasing. As I go to the right along the x, the function appears to get larger and larger. Okay? And so to be fully technical here, when I say that the exponential when I say that the exponential is increasing, and in particular in this particular example, for example, I'm talking about the following fact. For b greater than 1, the expression b to the x power is strictly increasing. That is, if x1 and x2 are real numbers, and if x1 is located is less than x2, but graphically, by our conventions, less than is to the left, greater than is to the right. So if x1 is less than x2, or informally, if x1 is to the left of x2 on our graph, then b to the x1 is going to be less than b to the x2. So in other words, if I let this be my x1, for example, then this height would be my b1. Would be my b to the x1, right? And that will be smaller than this. Then, like, if this is x2, this height would be my b to the x2. And so what it's saying is that as long as the x1 is less than the x2, the b to the x1 will be shorter than the b to the x2. Okay, that's an important fact. And now the reason why I said informally if x is to the left of x2 is that if you can imagine, there might be some, if you can imagine some alien civilization, or humans, or let's say that humans had in some point in history, instead of making the number line go negative to the left, positive to the right, it could have easily been reversed. Then this statement as written would still hold. But in that scenario where the positives are on the left and the negatives are on the right, in that scenario, x1 less than x2, instead of reading it informally as x1 to the left and x to the right, we would have, in that alternate scenario, written it as x1 to the right of x2. Okay. But okay, but anyway, that we're not in that civilization, and we're not in that like alternate scenario. We're in the scenario that we're in, and that means that negatives are to the left, positives are to the right. That means numbers get less than as we go leftwards, numbers gets bigger as we go rightwards. And so if I want to read x1 less than x2, I can feel comfortable reading it, well, comfortable knowing that I'm stating it slightly informally as x is as x1 if x1 is less than is if sorry about that, I was getting stuttering there. If x1 is to the left of x2, if x1 is less than x2, then the b to the x1 is less than b to the x2. Okay. Okay. My advice is just read it properly. X1 less than x2. But if you want to, you can also read it like kind of informally. But I recommend reading it properly all the time because it'll help develop your brain. And so with that, we're gonna let this example go. Now, if you wanted to make an index card for these functions in the event you want to use these for graphing by function transformation, I would of course write down the function that you did. I would write down this function, y equals 2x, or alternatively, you could write it as f of x equals 2 to the x power. You would write the domain, you would write the range, you would write the location of the horizontal asymptote, you would write this table, and you would draw the graph. Okay? Because then using transformations, we could easily graph some transformed version of this function, okay? In any case, this will be our first example, and we're going to proceed to another example forthwith. I hope you've enjoyed this example, and I'll see you soon. Thank you.